Hello mathematicians. I thought we needed a little bit of a primer on polynomials. So what we're going to do here is go back, way back. I can't get that phrase out of my head at the moment because it reminded me of a song which was in the top 40 in 1972, the year I was in year 11, called the Troglodyte Song. You might want to have a little look up at that on YouTube. But what I want to have a look at is initially some long division, which is a technique that you may not have even have done in primary school. So we'll look at this with numbers to start with, just make a few observations, then move on to polynomials and see how we go. So long division, if we think about the process of dividing. Well, I know we all have calculators now, which is probably why we don't do it. Say this number, and I wanted to divide it by 18. Then way back at school, we would do this. We would say 18 into 22 goes once 18, and then we would subtract that. If we got more than 18, we'd know that we'd made the wrong guess up here. But then we just simply bring down the next number, so 45. 18 goes into 45 twice. Twice 18 is 36. Bring down the 9, subtract that, get the 9, and bring down the 6. 18 goes into 96 5 times. 5 18s are 90. So we've got 6 left over. So obviously 18 won't go into 6. So we have a remainder of 6. And that means that we could say 2,256 divided by 18 equals 125 and a remainder of 6. And we would sometimes write that as 125 and 6/18, or obviously 125 and 1/3. From our perspective, what's more important is that we can write it in terms of what's called the division transformation. So I can say 2256 actually equals 18, so the thing that I'm dividing in, times 125 plus 6. This structure is something that we'll use in polynomials, where we can express one polynomial as a product of a couple of others, and there may be a remainder. Okay, so now I'm going to change things a little bit. So I'm going to say I'm going to be dividing my 18 into this number, 2,250. So I go through the same process and I get down to this stage, but when I bring the number down, that's a 0. And the 18 goes into that 5 times, so I get no remainder in this particular problem. So what that means is that my 2250 is equal to 18 times 125 exactly. So if I get no remainder, it means that 18, and for that matter, 125, are both factors of 2250. Now, we know that there are other possibilities as well, but these two are definitely factors of 2250. So this concept also we'll come back to. So now let's move on and actually have a look at polynomials. So what we have written here is a polynomial. So this polynomial, the thing that makes it a polynomial is that we have positive integer powers of x, and I guess we could include x to the 0 just here, so that's a condition for a polynomial. And each of these integer powers of x has a coefficient. The coefficient with the highest power is called the leading coefficient, and the coefficient of the power of x to the 0 is the constant term. So this polynomial is a function of x, so this is our function notation from early in year 11. And we know that this polynomial could be written in other ways. We also know that it may be possible to find when that polynomial actually equals 0. And when it equals 0, they are the zeros or the roots of the polynomial. Geometrically, they're the places where this particular polynomial, if it was sketched on the xy plane, would cut through the x-axis. So let's think about what the values of x actually are that make this statement true. What are the values of x which make p of x equal to 0? Well, we could get them lots of ways, but let's just do it the most formal way, which is our quadratic formula. So that would be minus b plus or minus the square root of b squared minus 5 squared. I want that to be a minus actually for my example. So minus 4ac, so that will be plus 24 over 2. So that's 5 plus or minus root 49, which is 7 over 2. So that will give me 12 on 2 and negative 2 on 2. So x equals 6 and minus 1 are the zeros of the polynomial. So if, for example, I took p of 6 and I plug that in, then I would get 36 minus 5 times 6 minus another 6, which is 0. So this illustration here, the fact that p of 6 equals 0, is an example of the remainder theorem, which is that if I get a remainder of 0, this thing is a root or a factor. If I plug in something else, which isn't a factor, I will get a remainder. So let's look at p of 2. Now actually let's go in another direction. Let's recall the link between roots or zeros and factors. So if these are the zeros, then our factors are x minus a root, x minus the other root. So these two here are factors of p of x. So I could write p of x like that as a product of two terms, product of two factors. You can satisfy yourself that if I multiplied those back out, I would get my original polynomial up here. So factors and roots, we need to make the distinction between them. And in fact, the factor theorem in your note somewhere says if x minus alpha is a factor, then alpha is a root and p of alpha equals 0. So those relationships we need to be comfortable with. Now what happens if I take the polynomial of something which is not a root? Then say I know that 2, for example, I think 2 is not a root. So if I take p of 2, that will give me 4 minus 10 minus 6, which is definitely not equal to 0. And in fact, and therefore 2 is not a root. And what it is equal to is minus 12. Now what's interesting is that not only does it show us that 2 is not a root, and therefore x minus 2 is not a factor, but it shows me the remainder of minus 12 if I actually divided x minus 2 into my polynomial. So that's what I'm going to have a look at now. So I'm going to take my polynomial that I had before, x squared minus 5x minus 6. I'm going to divide it by something which I know won't go evenly, the x minus 2, and see what we get. Before we even do that though, let's have a look at what would happen if I took my polynomial and divided it by something which did go evenly. So I knew, for example, that x plus 1 was a factor because minus 1 was a root. So if I do my process of long division, this x will go into x squared x times. I multiply that then, so x times x gives me x squared, x times 1 gives me x, and then I subtract. So minus 5x minus x gives me minus 6x. Then I bring down the next term, minus 6x minus 6. If I then divide x into this, it will go minus 6 times. Minus 6 times x plus 1 gives me minus 6x minus 6. And that's a remainder of 0. So what I see then is that I could write, so my division transformation, x squared minus 5x minus 6 equals x plus 1 multiplied by x minus 6, which we know is the case. So let's get back to this one here. If I divide my x into this, it will go x times, multiply it down, x squared minus 2x, minus 5x minus 2x will give me minus 3x. Bring my 6 down. X will go into this minus 3 times, so minus 3 times x gives me that. Minus 3 times minus 2 gives me that. The x's go out, minus 3x is 0. Minus 6 minus another 6 gives me minus 12. So what do I then notice? I then notice that x squared minus 5x minus 6 could be written as x minus 2 times x minus 3 with a remainder of 12. So what has all of that told me? Well, first of all, it's told me that neither of these are factors because they don't divide in evenly. It's told me that if I do divide one or the other in, I will get a remainder of negative 12. And that is also what I would get when I take, as we saw on the previous slide, p of 2. So p of 2 will give me 4 minus 10 minus 6, which is negative 12. So I could discover the remainder straight up. To actually get these, of course, I had to do long division. Now what we have there then is a set of really powerful tools. I can take a polynomial, I can almost guess whether something is a 0. I can check that by using the remainder theorem. So taking, substituting the root into the polynomial. And if I get the answer of 0, then it is a factor because there is no remainder. If I get a non-zero answer, it's not a factor, and therefore x minus 2 is, if I get a remainder of 0, it's not a factor because I have a remainder, and therefore x minus 2 is not a factor. I think I've just said that wrongly again. 2 is not a root, so x minus 2 is not a factor. Now, I'll just extend it to one cubic example, then I'll leave it till we get to the next part. Okay, so suppose I had this polynomial, a cubic, and I was asked to find the zeros, in other words, where this particular polynomial cuts the x-axis, if I was to draw this sketch up. And I was asked to write this in factorized form. Now, I have no tools in the ordinary maths course to help me, but I can combine the skills that I've picked up on our previous stuff about the remainder theorem and the factor theorem to start working on this. And I'll throw in one more, which we'll come across fairly quickly. And that is that when I do my initial guesses, if this particular polynomial has an integer root, and they certainly don't all, but if it does, then that integer will be a factor of plus 6. So that it could include plus and minus 1, plus and minus 2, plus or minus 3, plus or minus 6. And in theory, we just guess each of those. We use our remainder theorem so that we say, for example, p of one of these, and we see whether we get 0 left over. Now, because I've fudged this example, I know that 1 is a root. So if I take p of 1, that will give me 1 minus 6 minus 1 plus 6, which comes out to be 0. So that I know that 1 is a root, therefore x minus 1 is a factor. So if I know that x minus 1 is one factor, then what I can do is do my process of long division. So when I do this, x goes into x cubed, x squared times, multiply that down, I'll have x cubed minus x squared, minus 6x minus x squared will give me minus 5x squared. Bring down the next, which is that. X will go into this 5x time, or minus 5x times. So minus 5x squared plus 5x minus x minus 5x will give me minus 6x. Bring down that 6. X will go into minus 6x minus 6 times, minus 6x plus 6. So indeed there is no remainder as we expected, and therefore x minus 1 is a factor, and the other factor is this one. So I could say therefore p of x equals x minus 1 times x squared minus 5x minus 6. And then once I get down to the level of a quadratic, I have tools for working on that. And as we saw previously, that x squared minus 5x minus 6 is x minus 6x plus 1. So I've managed to fully factorise this polynomial, and I've found the 3 points where it cuts the axis.